Good morning, everyone, and welcome to the fourth Quantum Algorithm Seminar Series. And I'm Captain Yogendran, and I'll be the host today. As usual, if you have any question, please leave them in chat. And the speaker mentioned that he's comfortable with being interrupted during the session. So please raise your hand, and the speaker will address your question. That being said, I want to introduce you all to our speaker today, Martin Schuetz. He is a senior quantum data scientist at AWS. He completed his PhD in theoretical physics at Max Planck Society. So today he will walk us through about using combinatorial optimization with physics-inspired graph neural networks. So I'm going to hand it over to Martin, and show is yours.
Okay, thank you very much. Thanks for having me. My name is Martin Schuetz, and I'm a research scientist in the Amazon Quantum Solutions Lab. And so today I'd like to talk about how to solve combinatorial optimization problems with by fusing ideas from physics with kind of state-of-the-art tooling from deep learning in the form of graph neural networks. And as already mentioned, please, whenever you have a question, feel free to chime in. And I'd like to kick this off with sort of an executive summary on quantum computing. So really, what is quantum computing in a nutshell? So quantum computing leverages the kind of intricate and bizarre physical laws of the microscopic world to perform computations in novel and improved ways. Now, these physical laws, namely as dictated by quantum mechanics, they may seem bizarre and strange to us because we don't live in the microscopic world, we live in the macroscopic world, but these really have been tested again and again over the last few decades on single photons, single electrons, single atoms, and now thereby increasing more and more our confidence in this theory, and now kind of switching to a new paradigm where we try to leverage these laws to build actual machines. And that opens up a new paradigm in computing that promises to speed up solutions to certain hard problems. And really what we anticipate is not just a 10x performance improvement, just, like with your maybe next generation of GPUs, but really a 10 to the x exponential improvement for certain problems. Nevertheless, this has to be taken with a grain of salt, simply because building such a machine at relevant scales is an enormous undertaking, both from a scientific and an engineering point of view. So building up this quantum hardware at scale is really a tour de force, and we're just getting started. So what you see here, for example, is sort of one of the state-of-the-art quantum computers built here on IonQ, as you can access that today on AWS, where every of these little small blobs here represents one single ion, so a charged single atom trapped in ultra high vacuum. And that makes up a single quantum mechanical bit, a qubit, and sort of is the elementary building block of a quantum computer. But you can see we are talking about like 30 to 40 qubits here, and we will have to go to millions to solve commercially relevant problems. So sort of the era that we live in right now has been phrased as the noisy intermediate scale quantum era, which is still far from the end goal. But we can expect some promising first results, and now is sort of the time to get quantum ready for the quantum future once this technology fully unfolds. So what does it mean, noisy intermediate scale quantum era? Well, noisy because these qubits still are prone to errors simply because of noise. So, any sort of environmental effects that kind of disrupt the information that you encode in a qubit. These qubits are very sensitive to any sort of, outside magnetic field, electric field, So they have not sort of the error rates that we would like to have them eventually. And intermediate scale, simply because the size is not at the scale that we need to have them eventually. I mentioned hundreds of thousands to millions of qubits. Right now, we're talking about hundreds of qubits in state-of-the-art devices. Having said that, I mentioned that quantum computing eventually holds the promise to speed up solutions to very hard problems. So where do we expect some traction? So specifically, we expect quantum computing to have an impact in computational chemistry, in material science, and in optimization. Computational chemistry and material science is relatively easy to understand, simply because the underlying problems that you'd like to solve in many of these these domains are inherently quantum. So take, for example, drug discovery. So essentially, you have to solve for the optimal electronic configuration of a large molecule, and that is an inherent quantum problem. So essentially, you have to solve Schrödinger's equation, and there's no machine better suited to do that than an actual quantum machine that mimics and runs on these quantum laws that govern that are described by Schrödinger's equation. Optimization in itself, a large and very broad field of applications, where the idea, very broadly speaking, is that that a quantum algorithm can potentially scan the entire solution space simultaneously by the concept of superposition and entanglement, but that has to be taken with a grain of salt, because at the end of the day, we have to measure. So that's the connection from the microscopic world to the macroscopic world. We have to make a measurement, the wave function collapses, and we only get one single result per measurement. That is kind of a high-level overview, and really the upshot is that any of these, any of these quantum solutions will need a fault-tolerant quantum computer. A fault-tolerant quantum computer, meaning we have a recipe how to make these quantum computers essentially noise-free, how to essentially shield and protect them from undesired effects from the environment. And that is, and the name of the game is called quantum error correction. So essentially what you do is you encode a logical qubit in many physical qubits, typically with an overhead of 1 to 1000 or something like that. And sort of in aggregate, that makes the logical qubit very robust. But that tells you, that tells you that we will have to have millions of physical qubits to sort of tackle large-scale problems with many variables, as typically as we need to solve in practice to have any commercial impact and potentially sort of outperform classical approaches. Still, to help our customers at AWS get quantum ready, get familiar with this sort of emerging technology, we have built sort of a very comprehensive ecosystem around quantum computing that essentially consists of 3 pillars. So let me briefly walk you through these. First and foremost, we have launched Amazon Braket, basically with the goal to democratize quantum computing, really to take this technology out of the ivory towers at some universities, some institutes, and give it into the hands of our customers, all within one unified framework. So all fully integrated into AWS. It's essentially a collection of APIs as everything else on AWS, with security, networking, etc., all baked in, and giving you not just one technology, but we take a hardware agnostic approach, so you can have access to quantum computers based on ions, quantum computers based on superconducting qubits, special purpose machines that are tailored towards optimization, again based on superconducting qubits, along with state-of-the-art simulator that help to simulate quantum mechanical behavior on classical devices. All of that fully managed to make the life as easy as possible and get started very quickly for our customers. Still, we are cognizant of the fact that quantum computing is still in its infancy, and that is why we have basically launched our own R&D team. That is the Center for Quantum Computing. It's hosted at the campus of Caltech, where we simply try essentially to push the boundaries, try to give back to the community, actively contributing to the quantum community, pushing the boundaries of what can be done with quantum computing today and tomorrow. And last but not least, we have the Quantum Solutions Lab. So this is where I'm a member of, and that is essentially our customer-facing team. So it's a team of scientists with deep expertise in quantum computing that work side by side with our customers on specific problems, help them crack these problems with whatever is the best tool to solve these problems, and on the way sort of kind of transfer knowledge and IP and help you prepare for the quantum future. So the way that looks, the way this typically looks like is really, this is not a single shot, but it really takes our customers on a journey where we try to help you get quantum ready through training and enablement workshops, proof of concept, POC studies, all the way to a stage where you are enabled to build expertise and IP in this new emerging tech arena. But something that is very close to our hearts is that on the way, we also really want to have business impact today and help you scale up to larger problems that go beyond simple proof of concept studies. Again, because of the hardware limitations of today's quantum computers, really try on the one hand, deliver expertise, knowledge, IP today, but also on the other hand, really crack the relevant business problems today with whatever tool is best suited. So we really open up our aperture beyond quantum technologies. And that is very much the spirit for the talk today, because we're going to take ideas from physics and sort of supercharge them with state-of-the-art deep learning techniques to solve combinatorial optimization problems. Just to illustrate the kind of work that we do with some of our customers in industry, for example, to help BMW identify appropriate use cases within BMW that sort of lend themselves towards quantum or quantum-inspired solution strategies. We have helped them set up and design an open quantum computing challenge where everyone can participate. It's ongoing right now. So our participants can discover potential real-world use cases and then develop and test their solution strategies on Amazon Bracket in sort of a very hands-on way. There are 4 use cases that participants can work on. 2 of them are optimization use cases, how to minimize the number of pre-production vehicles you need before you run and finish all and complete all tests needed before a certain new car goes into production, how to in an optimal way place sensors around the vehicle, material deformation. Ideally, you would like to minimize the number of crash tests because these are very costly, by more performance simulations, and then a use case around quantum machine learning to improve quality assessment. So these are the kind of use cases that are explored right now by participants and are very relevant to BMW, and where we helped BMW to design and support this competition. Going a little bit away from this example, more broadly, the way we typically engage with our customers goes as follows. So we typically like to identify a very concrete target use case that we deem sort of suitable for a quantum computing solution strategy. We then build a prototype by developing new algorithms and approaches. Typically, this has to be done from scratch, simply because there are very few off-the-shelf solutions available in quantum computing today. And then in the next phase, we benchmark these prototypes against state-of-the-art classical techniques, either coming from HPC, high performance computing, or machine learning, because simply to cut through the hype and give a transparent view of where quantum computing really is. And only by having available sort of these benchmarks, I think you can build a solid quantum strategy and roadmap for your company within this field. And then finally, we wrap up with results, typically internal reports or even some peer-reviewed publications. But looking at this engagement model, what we learned is the great majority of target use cases are optimization use cases, specifically combinatorial optimization use cases. And sort of the gap that we identified is that there wasn't sort of a one-stop shop solution, sort of a broadly applicable framework to solve these kind of combinatorial optimization problems with state-of-the-art machine learning and deep learning tool. And that is where we, I think, combined ideas in a very interdisciplinary fashion, drawing from concepts from computer science, from machine learning, and from physics to solve these optimization problems, and thereby making a contribution at the intersection of these four research disciplines that are typically distinct and that we try to unify here to come up with a new and clever solution strategy. To walk you through the solution strategy, I first like to set the stage and talk a little bit about networks and graphs. And networks are really a fascinating concept because essentially they touch upon every aspect in our life, with a network being a collection of objects where some pairs of objects are connected by links. So a prototypical example could be social networks. So think about Twitter, think about Facebook's, where the nodes in your graph correspond to the social members of the network, and edges correspond to social ties, friendships within this network. Then again, in a completely different domain, completely different length scale, you can use graphs to model molecules. So for example, in drug discovery, where now the nodes of your graph correspond to atoms and the edges correspond to chemical bonds between these atoms. Then again, completely different application area. Obviously, you can model transportation networks as a graph, where now, for example, the nodes in your network correspond to bus stops and edges correspond to streets, roads connecting these bus stops, and so on and so forth. Really a gigantic plethora of real-world scenarios that fall into this broad class of networks. And now there are a few standard ways to analyze networks. So what are the kind of typical problems that people study in the network community? One of them is node classification. So for example, predict fraudsters in social networks. So you would like to, for every node, you would like to classify this node as a fraudster versus non-fraudster. Link prediction, take for example, the future interaction and recommender system. So whenever you go on Amazon, that is the kind of prediction. If you are recommended different items for your next purchase, this is what happens behind the scenes, kind of link prediction. Community detection, identify densely linked clusters of nodes, clusters of fraudster rings, for example. And so on and so forth. But what we will focus on today, and that's why it's highlighted here in orange, is sort of this this problem of node classification. So we'd like to assign every node in the underlying graph to a certain type, or often called color or class. Like for example, in binary classification, for every node, we're going to identify this node as a fraudster or non-fraudster. And next, I'd like to briefly talk a little bit about combinatorial optimization in itself, a large and very broad, diverse field of research. Combinatorial optimization is one of the most important areas in the field of optimization. Practical applications can be found virtually everywhere. Transportation, logistics, finance, manufacturing, and broadly speaking, it describes every setting where a large number of yes and no decisions must be made, and each set of decision then yields a corresponding objective function value, like a cost or a profit, and you would like to optimize now, minimize the cost or maximize the profit, for example. But you're facing typically you're facing an overwhelming number of decisions that scales exponentially with the number of variables, so something that you cannot do with sort of any brute force enumeration technique. And to be a little bit more concrete, I'd like to introduce this field of combinatorial optimization with a sort of somewhat real-world example, and that is how to find a risk diversification strategy in the following setting. So let's consider the following scenario. So we are given a universe of 8 stocks. These are labeled with 3-letter tickers, A, B, C, and so on, together with information about correlations between these stocks. So for example, we know that stock A is correlated with stock C, F, and H, and so on and so forth. So this is information typically drawn from historic data from the stock market. And so the problem we like to solve is find the largest set of uncorrelated assets. That is a viable risk diversification strategy, as some of our finance customers would like to implement for their customers. Now you see already for this kind of toy model with just 8 stocks, we have in principle 2 to the 8, 256 solution candidates, because for every asset, we have to make a binary decision whether to buy or not to buy this asset. In principle, we could enumerate through 256 solution candidates, but obviously this becomes tedious and basically impossible as we scale up the number of variables because of this exponential blow up here. So for 100 assets, you would have 2 to the n potential solution candidates. So that is a number that you cannot go through on an individual brute force basis. Together with the fact that this list of historic stock correlations becomes tedious and hard to and unhandy very quickly. But that is where graphs kick in to sort of get a grasp on the situation, to visualize the situation, but also as a tool for further analysis. So what we've done here is we have a graph where every node of the graph corresponds to one asset, and edges, these black edges correspond to correlations between these assets. So for example, you see here that stock A is correlated with stock H, stock F, and stock C as written down here, and so on and so forth. So now this graph visualizes this situation, and what we like to do is find the largest number of assets that is uncorrelated. Now it turns out that maps onto a famous canonical problem in discrete mathematics or in graph theory, and that is the NP-hard maximum independent set problem. The maximum independent set problem is the following: find the largest independent set, where an independent set is a subset of nodes that are not connected with each other. So you find, for example, this could be a valid solution. It's an independent set of size 2, because we, out of 8 nodes, we have colored 2 in red, and they are not connected to each other. So this would be a potential strategy. Out of these 8 stocks, we decide to buy 2 of them, and they are not directly correlated with each other. Turns out you can do better. You can find a basket of assets made out of 4 stocks. You can, if we color these 4 nodes here in red, because there is no edge connecting any of the red nodes directly. So to mathematically formulate a cost function, so something that we can then try to minimize, we typically like to make use, and this is where now physics comes into play. We'd like to make use of the concept of a Hamiltonian. That's really the bread and butter in physics, in quantum computing. Essentially, for the sake of this talk, you can equate Hamiltonian with a cost function. the concept of a cost function. So really what it does, for any potential configuration of variables, for any potential coloring of your graph, it gives you a number. And the number tells you how good you're doing. The lower, the better, because typically we like to minimize energy. And for this particular problem here, for the maximum independent set problem, it's relatively compact. It consists of two terms, where the first term is sort of a reward function. So for every asset that we put into our basket, we're going to set the corresponding binary variable to 1. So this is the kind of encoding we did here. So we introduced binary variables. They can only take on two values, 0 and 1. And basically, in terms of coloring, we say if a node is white, this corresponds to this variable being 0. If it's red, it corresponds to 1. So if we set a variable to 1, if we color it in the graph in red, we score a point here in the first term. But we get penalized whenever we try to put two assets into our basket that are connected by an edge. That is essentially what is described here by the second term, a penalty term that will sort of bump up the energy, make this configuration sort of less desirable whenever we violate this condition of having correlations in our underlying asset basket. And just to give you a few examples, in principle, we could decide to color known nodes. That would be an energy of 0. If we decide to color these two nodes, we score 2 points and we don't have any violation. We get an energy of -2, so we do better. That is, this is what the energy is telling us here, the Hamiltonian, the lower, the better. And turns out that an energy of -4 is the best we can do in this scenario if we color these 4 nodes here in red. Again, this is a toy model example just to illustrate the field of combinatorial optimization. In typical use cases, as seen with our customers, we don't have 8 stocks, but we have hundreds or thousands of stocks. But already, if you consider 300 nodes, a problem with 300 assets, in principle, you would have 200 to 300 candidate solutions. That is a number that is larger than the number of particles in the universe. So certainly something that you cannot solve with any type of brute force technique, and where you have to rely on sort of heuristics that provide good approximations, high quality solutions to these kind of hard problems. Just to close the loop on this example, so we have now solved the maximum independent set problem on this graph with 8 nodes. And essentially what it means is, coming back to our use case, it means that we buy stock A, stock B, stock D, and stock G. And that is an asset of 4 assets out of 8 assets without any correlations between these. And that is an optimal solution to kind of the problem that we were facing at the beginning. There are many more problems of this kind of type. I've listed a few of them here: maximum cut, minimum vertex cover, maximum click, etc., etc., etc. And these are really not just academic problems, but they map onto real-world practical applications: data clustering, security monitoring, risk diversification. The list goes on and on and on. And sort of what we do at the Quantum Solutions Lab is, once we have identified a pain point in your organization, is try to find a mathematical model that represents this problem and try to map that onto one of these kind of canonical problems, and then build the optimal tools to sort of find high quality solutions to these kind of hard problems. So this is a long list of problems, but it turns out that there is one unifying framework, and that is called QUBO. QUBO is an acronym. It stands for quadratic unconstrained binary that unify a rich variety of these NP-hard combinatorial optimization problems. Again, prototypical example: assignment problems, capital budgeting problems, task allocation problems, etc., etc. And it is inherently linked to physics, because there is a one-to-one correspondence between QUBO problems and the famous Ising problem, Ising Hamiltonian in physics. And that is really a one-to-one mapping. It's essentially the same thing. It's just a matter of taste whether we prefer to encode your binary variables using 0 and 1, or using that is the preferred language in physics if you denote these as bins with values -1 and 1. But there is a mapping, a simple mapping that which you can use to go sort of back and forth between these two sort of modeling approaches. But with all the understanding and knowledge built around Ising Hamiltonians, that is obviously something we can leverage here to solve these cubo problems in practice for our customers. The cubo model itself is surprisingly compact and simple. It is a Hamiltonian that you try to minimize, and it is quadratic in these binary decision variables that take on just two values, 0 and 1, and essentially your entire problem is encoded into one matrix, typically denoted as Q, the cubo matrix, and that really captures the essence, the problem that you'd like to solve. Again, if we consider the example we've looked at before, for example, the maximum independent set that we wrote as shown here, this is a quadratic Hamiltonian, quadratic in the binary decision variables, so something that falls within this broader framework of cubo problems. Okay, so we talked about networks and graphs. We talked about combinatorial optimization problems and how to frame combinatorial optimization problems as optimization problems on graphs. Let me now introduce a new tool that has emerged in the last few years in the concept of deep learning, and this is graph neural networks. So graph neural networks are an emerging family of deep neural networks that sort of extend the standard toolbox in deep learning. Because if you think about it, deep learning by now has certainly matured into a technology that is commercially viable, but it has done so specifically in the fields of computer vision, where you deal with images, and natural language processing, where you deal with text. But if you think about a little bit more deeply for a second, turns out that these are very rich data structures. Yeah, you can think of an image as essentially as a function on a two-dimensional Euclidean plane sampled on a grid. You can think of text as a one-dimensional grid, whereas these networks and graphs that, you know, as they show up in social networks, as they can be used to model molecules, etc., they can have arbitrary size, complex topological structure. There's no fixed node ordering, no reference point. So something that does not readily fall into the kind of the standard toolbox of deep learning. And that is where now graph neural networks come in and shine, essentially by building representations of nodes and edges in graph data. And the way they do this is as follows. So essentially you attach an embedding vector labeled called H to every node that sort of internally represents the node. And now you go through a process typically called message passing or neighborhood aggregation, where every node collects information from its direct neighbors, with the neighborhood defined by the topology of the graph. So you only basically gather information from your direct local neighbors. You aggregate this information, and then you pass this through a nonlinear activation function, as you typically do in deep learning, to update the internal representation of a node. So all of that happens on a local scale, but once you repeat this step by essentially stacking several graph neural network layers, you can enable the model to sort of open up the receptive field and have information propagate essentially across the entire graph. So just to illustrate that once more here is, if you could just consider this red node here in this graph, typically a graph neural network layer will first capture within a one-hop ring, will capture information from its direct neighbors. But if you repeat this step, you essentially, in the next step, you aggregate information from the yellow colored nodes and so on and so forth. So by stacking layers, you can propagate information essentially across the entire graph. and also thereby have nodes talk to each other that are not directly linked. Okay, so now we have put together all puzzle pieces. So let me maybe pause here for a second. Is there any questions so far? So on a high level, we have talked about graphs, we've talked about combinatorial optimization problems, and we have talked about this new tool of graph neural networks that sort of accepts graphs as input structure.
I just had a quick question.
Mm-hmm.
So the slide just before this one.
Mm-hmm.
So I'm assuming each of those nodes represents one of the securities in your example, and then you're changing the weight of the link to describe whether or not they're correlated or not. Am I understanding that right?
So what we, okay, so more or less, okay, so let's talk about this asset example here once more. You're right, so the nodes correspond to the assets. And so every node is represented by an embedding vector. Yeah. At the final layer, this will be the decision, black and white, red or white, whether to buy or not to buy the stock. And it talks primarily in first information from the nodes that it is connected to, and these are the that it is correlated with. But by extending, sort of going beyond one hop, you also talk to assets that you're not correlated with in the next round of iterations, and therefore you get kind of a global aggregation of information whether or not essentially you should then buy or not buy a specific asset. But sort of the returns and the correlations in this example, they are fixed. They are not optimized. It's the only optimization you do is whether, given these correlations, represented here by edges, which assets should I buy or not buy? Should I, in other words, which nodes should I color in red or not?
Gotcha. Thanks.
Okay. Yeah. So now I can. So now essentially we have put together all the puzzle pieces to sort of highlight what we did in our recent work, where we show how to use graph neural networks to solve these types of optimization problems. And really, the essence of this work, the key idea is to frame combinatorial optimization problems as an unsupervised, that means we don't need any labeled training data, node classification test. Because what we saw is, for example, in this asset optimization problem, is that for a given graph, essentially we have to make a binary decision for every node, whether to buy or not buy, whether to color a certain node black or white, as shown here. But that is a hard task, because once you have 100 assets, you will have to make 2 to the 100 decisions, something that you cannot just go through and solve in Excel or something. So you have to do something more clever. And that is where we propose to do that with an iterative training strategy using graph neural networks that directly operates on the underlying graph with a with a custom loss function that encodes the specific optimization problem. And what we do here is, so we take the concept of a combinatorial Hamiltonian, a cubo-Hamiltonian, and translate that in a one-to-one mapping to a custom loss function, with which we can then train the weights and update the representation of the graph neural network. So essentially what we do, the trick that I just described, is rather than dealing with binary variables as we do in the underlying optimization problem, because these are typically discrete problems. Take BMW, they cannot build a 3.5 cars. They can build 3 cars or 4 cars, but not 3.5. Nevertheless, throughout the training strategy, we sort of disregard this integrality constraint and relax these variables to a soft probability assignment, something between 0 and 1, because then we have continuous quantities And that allows us to tap into the standard toolbox of deep learning using then standard backpropagation to update the internal weights and embeddings in the graph neural networks. Once the training completes, we project these soft probability assignments. So the graph neural network is going to say, there's an 80% recommendation to buy a certain asset, and we then going to flip the switch and say, okay, buy this asset, 1 or 0. The entire flow chart illustrating then, so sort of the end-to-end workflow looks as follows. So you model your problem in terms of a graph, as shown here, a graph with 5 nodes, 6 edges. You define your underlying problem you like to solve, for example, in terms of a cubo-Hamiltonian, and that really captures a large class of optimization problems. So you have here the only figure of merit you need here for this problem definition is the Q matrix. It's shown here for the maximum cut problem and for the maximum independent set problem. And we then feed this together with a training strategy that defines our graph neural network ansatz, hyperparameters, etc. We feed this into our GNN optimizer that then performs iterative rounds of message passing, so neighborhood aggregation and updates, training against a custom loss function that stands in a one-to-one correspondence to the original Hamiltonian. Once training completes, we get soft probability assignments as schematically depicted here with these shaded colors. And then to come back to the original integer problem, we sort of take these proposed assignments and make them hard assignments. So every node now is either colored black and white, and that is essentially the final bit string that represents the solution to your combinatorial optimization problem. Zooming out a little bit, all of that fits into an end-to-end workflow within a sort of encode, process, decode framework. So what we do first is we take a business problem in your organization, say some stock problem, some marketing problem. We model that mathematically, we feed all of that into this framework, and then we decode the solution again back to the underlying use case in finance. You know, that could mean this 5-node example could mean buy the white colored stocks 1 and 2 and do not buy stocks 0, 3, and 4. For underlying marketing problem, that could mean run campaign A with customers 1 and 2 and run some campaign B with customers 0, 3, and 4. So with that, we've covered the whole framework as described in our recent research paper. I haven't told you how far this is actually doing, how good this is actually doing, and what we found is it does very, very well. So here's a example trying to solve the maximum independent set problem, the problem that we distilled previously in the asset problem. Again, the problem is to color as many nodes in orange or in red as possible, and that will be the size of the independent set. With the GNN here, we find 42 nodes that we can color in orange out of 100 in this larger graph with 100 nodes. Whereas, so something superior to the solution that we find with a traditional solver based on the Bupana-Halterson algorithm that only proposes a solution with 37 nodes colored in red. We have done this more systematically for a large class of problems. So this is here the maximum independent set size as a function of the graph size, the number of nodes. What we find is that for small graphs with hundreds to thousands of variables, we perform on par or even better than traditional solvers, so existing algorithms that don't leverage graph neural networks. But we can really push here the boundaries and essentially enter uncharted territory. I'd like to highlight here this number here on the right that indicates that here we solve a problem with 10 to the 6, 1 million variables. So something that was not possible before with kind of standard techniques. So we are actually in a situation where we cannot benchmark, compare our results to other solvers simply because that is uncharted territory. The only thing we can do is we can compare our results against known upper bounds, so sort of asymptotic limits, and we find that we get very close to these, so about 90% approximation ratios. And we do so in surprisingly striking fast timescales. So we can solve problems with millions of variables in about 10 to 15 minutes on modern GPU instances, again, on classical compute, not a quantum computer, but taking ideas from physics, physics inspired, supercharging them on classical compute to solve sort of industry relevant problems today. And we can do so very quickly because we see a very moderatively scaling of the runtime with a function of the node, so polynomial scaling with a mild exponent. Whereas if you contrast that with the traditional solver, the benchmark solver, it actually does faster or for very small problems with hundreds of nodes, but it does so with a polynomial scaling that has a larger exponent. So if you extrapolate that and continue this line, you see that very quickly you run out of steam, and you cannot solve kind of problems with millions of variables using these traditional techniques, simply because this would not complete in any reasonable runtime. We've done some further benchmarks showing that this appears to perform very well on the canonical maximum cut problem. It's similar to the maximum independent set problem, but describes other use cases, again, and known to be NP hard, so something you cannot solve exactly. And we find for intermediate node sizes, so these are some benchmark graph instances with thousands of nodes, we are very, very close to the state-of-the-art results, where some of these are special purpose algorithms tailored towards solving this specific problem, whereas our approach is a general purpose solver. It can solve any type of cubo problem or even beyond that. With that, let me conclude. So in summary, I tried to show how to solve a large class of combinatorial optimization problems by using ideas from physics. So we talked about this idea of formulating your problem in terms of a Hamiltonian, and sort of fusing that with ideas from from deep learning in the form of graph neural networks to solve these hard problems. It is a general purpose solver, and it appears to be very performant and very scalable because we can solve problems with millions of variables on a single machine, and we have ideas how to go actually extend it to hundreds of millions once we go to distributed training. We plan to continue this sort of applied research at the intersection of these 4 research fields. For example, we have ideas how to solve fraud detection within this framework using some physics-inspired ideas, but also continue some outstanding fundamental questions, again, through the physics-inspired lens of phase transitions in a way there where we think we can make a contribution to this field. And with that, I'd like to thanks everyone. Thank you. Thanks for listening in. I'm happy to take questions if there are any.
Thanks, Martin. So if you have any question, please unmute yourself and ask.
Hi there, Major Turnish from D&D, Dimsker. Yeah, I'm just wondering what we can do currently in the Amazon cloud with the current state of the quantum computing that's available.
Yeah, good question. So you have full access to Amazon Bracket. It's our dedicated quantum computing service. It is sort of a unified user experience, because you have to see quantum computing was very much fragmented landscapes till, I would say, Amazon Bracket came around. Yeah, so you had different devices, different programming frameworks, and now essentially we provide a one-stop shop, so you can program these different devices all within one unified language. And so if you log into Amazon Bracket, you can spin up with a few clicks your own notebooks. We have tutorials how to get started on quantum computing, and then we give you access, to the current state of the art of quantum computing. So we have right now, we have 3 quantum computers available, and these are 3 different hardware paradigms. Again, we are hardware agnostic, and this is just the starting line. We will extend this portfolio in the near future. So we will add on other technologies, other quantum computers as these mature, and we're also building our own quantum computer, and that will be given to the into the hands of our customers through Amazon Bracket.
Okay, thanks, Martin. Yeah, I was wondering what kind of simple problems can we do with the current system?
Yeah, good question. I mean, you can, for example, I talked about this broadly applicable Cubo framework, right? It is one common framework for all types of optimization problems. And essentially, it's here, this slide. And we have, for example, we have a machine called D-Wave, and you can access that through Amazon Bracket. It actually comes from Canada. It is a special purpose machine with 5,000 qubits that is tailored towards solving this type of problem. With 5,000 qubits, there's a caveat, but this goes probably beyond the scope of this session here, is that once you try to embed your logical variables, your Cubo problem, onto the D-Wave chip by mapping a logical binary variable to a qubit, there's a certain overhead because, how to say this? Because the underlying chip is sparse, and you have to sort of and sometimes the problems are all-to-all connected. So there's an overhead where you map one logical variable to many qubits. So you can maybe solve a problem with 150 logical variables on today's D-Wave chip. And that is why, very often you can do this to build a proof of concept, but then more often than not, our customers want to go beyond that. And that is where we then offer these kind of physics-inspired solutions that run on traditional hardware. That is also something you can run on AWS, most certainly. These kind of deep learning solutions that I, described here.
Okay, thank you, Martin.
Eddie, I see your mic is on mute. You're going to ask a question? Okay. In that case, I have a couple of questions. So how is this compared to the QAOA? Like they both seem to solve the max cut problems, right?
QAOA, yes. Okay, so max cut, first and foremost, is one of these Cubo problems, similar to the maximum independent set that I described. So it is essentially an Ising-Hamiltonian. One strategy to solve that is using QAOA. So that is a variational hybrid algorithm on that runs on a circuit-based machine. And you can do that. Yep, certainly you can do that. But you will be able to sort of run on today on maybe 50 variables, because every variable will be a qubit, and the current size of quantum computers is about 50 qubits or something like that.
Okay.
So it's you can compare. That's the kind of proof of concepts that we do. Compare QAOA to the solution that I focused on today, and then go beyond that using these kind of physics-inspired deep learning tooling.
Okay. So another question I have is, so I work for the land equipment side of things, like how do we keep our fleet running and how do we optimize our logistics and supply, things like that. So is a QSL open to share some of the findings with, let's say, B&W, so we can build our case to look at the similar solution?
So we have certain, I mean, I think this would be that would be a good conversation in another call. So we have kind of a deck with use cases. So problems that we have worked on with customers in the past. You know, some information we can share, some information we cannot share. That is like based on the agreements we have with our customers.
Yeah. So it's more like saying like using this solution, like we increase. This is the results we found. We don't need to go into details about like all this technical stuff just to get like using this improved our system, right? Or not improved system, our process and things like that. So which will allow us to build a case of why my director general needs to look into this, right? So something like that to build a case. Okay.
Yeah.
Right. I'll send some emails to you then.
Yeah. Let's follow up in an email. Unfortunately, I have to jump. I have another call now at 12. Are there any other urgent questions?
Well, one more from one more question.
So I you have to excuse me. I mean, I'm not a data scientist or a quantum scientist.
Sure, no worries.
I'm representing those clients in the national security sort of space, and I'm still trying to understand. I'm trying to wrap my head around. So, where's the quantum in this graph neural network? So, are you replacing the activation function of the neural network node with a quantum qubit, or
there's we don't need any qubits here. This is not a quantum approach. So
okay, so it's just a Hamiltonian.
We deem it physics inspired because we use the language of a Hamiltonian. So you need to be familiar with the concept of a Hamiltonian, but that is something that was known before quantum physics, right? That is also known already in classical physics. So that's why we say physics inspired, because in statistical physics and so on, they've used Hamiltonians for centuries.
So you're just using normal compute here.
That's right.
Because you mentioned the D-Wave. You mentioned the D-Wave computers. So I'm just.
That is the D-Wave. D-Wave is a different backend available on Amazon Bracket to try solve these QUBO problems with using a concept known quantum annealing. And there you need qubits. It is a quantum machine, but it is complementary to what I presented here.
Gotcha. Okay, great. Thank you very much.
Thank you. Okay.
That's it. So thank you very much, Martin, for taking your time to explain this.
Thank you.
And I'm pretty sure the attendees really enjoyed this session. So yeah, thank you very much, and talk to you later.
Thanks, everyone. If there are any questions, we can follow up on email. Sorry, I have to jump.
Sorry.
Thank you. Have a good one. Bye-bye.